In this review video, I'll be introducing Unit 2 on elements and compounds. First, we'll start with a review of the periodic table. If you look in your textbook on the front cover, you will see that there is a periodic table that's listed there, and I recommend that you add some notes as we go along talking about the periodic table, because it's a great resource to look back on as you're working through this unit. If you take a moment to look around the room that you are in at this time, everything that you can see and feel and smell and taste is made up of matter. And all matter is made up of elements that are listed on the periodic table. Now, matter can be made up of just one singular element, or it can be made up of a combination of elements to create compounds. Each element that is listed on the periodic table is listed in its own box, and the symbols and numbers in the box help to characterize the element. Each element is numbered, so we start with hydrogen, which is element number 1, and then moving over and down the periodic table all the way to number 103, which is element lawrencium. Element hydrogen is the lightest of all of the elements, and element lawrencium is the heaviest of all the elements. Each element on the periodic table has its own specific atomic structure, and that's what we're going to be talking about next. Each element in the periodic table has its own specific atomic structure. The atom is the basic unit of a chemical element. It is made up of protons, which are seen here as the blue particles in the atom, and they are located in the nucleus of the atom, and they are the heaviest of the particles, and it's these protons that give the atom its weight. Next up are the red, which are the neutrons. They're also very heavy particles, which also add to the weight and are found in the nucleus. The neutrons do not have a charge and help to keep the protons from repelling against each other. They're like the glue inside of the nucleus. And then lastly, the third particle that we look at are the electrons. And the electrons are very, very small. They have very little mass, and they have a negative charge. And they're being pulled towards the nucleus by the protons. They orbit the nucleus in paths called electron shells. This diagram represents the atomic structure for a carbon atom. The carbon atom is, or the carbon element is element number 6 on the periodic table, and that's because it has 6 protons. So you can't see in this diagram all 6 protons. There are 2 hidden in the back of the nucleus, but it would have 6 of these blue positive particles for our protons. It also has 6 of the neutral particles of the neutrons. On the periodic table, carbon is represented in its own box with the symbol C for carbon, and it would have the atomic number 6. The atomic number tells us how many protons there are in the atom. The atomic number also tells us the number of electrons in the atom as well. So carbon has 6 protons. It also has 6 electrons. Underneath the symbol for carbon in the periodic table is another number, and carbon's number is 12.01, and that represents atomic mass. Atomic mass is the total number of protons plus neutrons that carbon contains. So to find out how many neutrons an atom has, you want to take the atomic mass and subtract the atomic number. So in carbon's case, the atomic mass is 12.01, and we'll subtract 6, and that gives us approximately 6 neutrons. So the periodic table gives us lots of information on the element just in the box. The number above the symbol is the atomic number. It tells you how many protons and electrons the atom has. The atomic mass indicates how heavy the atom is, and it is a combination of the number of protons and the number of neutrons. So if you take the atomic mass and subtract the atomic number, you're going to get the number of neutrons that the atom holds. Many elements on the periodic table have different versions of themselves. That is to say that although their number of protons always stays the same, it's their number of neutrons that can be different. So you need to remember that it's the number of protons that differentiate each of the 103 different elements on the periodic table. Number of protons never changes for each of the individual elements. However, different versions of the same element, although they have the same number of proteins, can differ in their number of neutrons. Let's look at the element neon, for example. Now, neon is the gas that's found in neon lighting. So if you've ever seen a neon sign, you'll see that it's a tube that contains the gas neon, and then electricity is applied to the tube and the neon lights up. Neon on the periodic table is shown as the symbol Ne, and it has an atomic number 10. So the atomic 10 means that it has 10 protons and it has 10 electrons. Neon will always have 10 protons in its atom. However, there are different versions of neon that have different numbers of neutrons. That is why when you look at the atomic mass of any of the elements on a periodic table, it is going to be an average of all of the neon atoms and their different numbers of neutrons. One version of neon has 9 neutrons. One version of neon has 10 neutrons, and another version of neon has 11 neutrons. And because the neutrons do have significant mass, it changes the atomic mass for each of these neon atoms. So on the periodic table, in order to get the atomic mass, they have to average out all of these versions of neon. Now, it's not as simple as just adding them all together and dividing by 3, and that's because the abundancy of each of these neon variances are different. And if you're wondering what we call the different varieties of neon, that's called isotopes. So an isotope is a version of an element that has a different number of neutrons. So protons always stay the same, but if the neutron varies, the neutron number varies, you have an isotope. So there are 3 isotopes of neon, one that has 9 neutrons, one that has 10 neutrons, and one that has 11 neutrons. When looking at a sample of neon gas, you can see that that sample of gas is made up of different isotopes of neon. Neon 21, there's only 0.27% of the sample is going to be that. Another isotope, neon 22, is only 9.25% of the sample. And then the rest of the sample, which is 90.48%, that's going to be neon 20. So when you average out the mass of all the isotopes within the sample, you're going to get the relative atomic mass of 20.18. And that is the atomic mass that is presented on the periodic table, but it's an average of all the different isotopes that are found in a single sample of the neon gas. So what you need to take from this idea of isotopes is that the number of protons in an element never changes. It's always consistent, it's always the same. But there are different versions of the elements, and those different versions, the neutron number will change. And when the neutron number changes, the mass of the element changes slightly. So this atomic mass that's given here in the periodic table is actually a relative atomic mass because it is the average of the atomic mass of all the isotopes in the sample, and those isotopes aren't it's not equal amounts of each of the isotopes that make up the mass. Some are going to be more prevalent and others are going to be less. So you have to keep that in mind in terms of how they get this average atomic mass. You can distinguish isotopes of an element using isotope notation. An isotope notation is always going to be the symbol of the element, and then it's going to be the atomic number of the element, which you can see I have 3 different neon isotopes here. I have neon 20, neon 21, and neon 22. The atomic number always stays the same because no matter the isotope, if it's neon, it's always going to have 10 protons. What does change is the atomic mass, because each of these is going to have a different neutron number. So for neon 20, we have 10 protons, but because the atomic mass is 20, that means that there are also 10 neutrons. So for the isotope neon 20, the symbol is neon with 20 and 10, 10 standing for the atomic number and 20 standing for the atomic mass. And then to find out the number of neutrons, we are going to take 10 away from 20, and that gives us our neutrons. For neon 21, again, our atomic number stays as 10 because neon always only ever has 10 protons. But for isotope neon 21, there is an atomic mass of 21, which means that neon 21 has 11 neutrons. So it's going to be a little bit heavier because of that extra neutron. And isotope neon 22, again, 10 protons, that never changes, but its atomic mass, is 22. So neon 22 has 12 neutrons. It's interesting to point out that the neutrons don't change the physical and chemical properties of neon. The only thing that changes chemical and physical properties are going to be the number of protons. And if you have a change in the number of protons, then the element changes. So up to this point, we've looked at how an element gets its mass, and we saw that most of the mass in the atom is located in the nucleus, and it involves the neutrons and the protons. They are quite heavy. Now, looking at the periodic table, the element with atomic number 1 has 1 proton, and that's hydrogen, and as you move across and down the periodic table, you get more and more protons and neutrons, and that's what creates heavier and heavier elements. What we're going to look at now is the electron configuration. How many electrons and where they're located in an atom help tell us how reactive an atom is. Atoms react with other atoms, and the more reactive they are, the more that they are going to combine with other elements and create chemical reactions. So the reactivity of an atom is very, very important because that's going to tell us how they react with other elements in the periodic table to create chemical reactions. Now, electrons have a negative charge, and they are attracted to the positive charge within each of the nucleuses of an atom. Or I should say the nuclei of the atoms. The plural of nucleus is nuclei. So the electrons are found in these electron orbits called electron shells. And as an atom has a greater mass, the number of electron shells that it has also increases. Now, electron shells have a limit on how many electrons that they can hold. So for instance, the very first electron shell in any atom can only hold 2 electrons before it becomes full. And that's because that first electron shell is quite small. All the electron shells after that first electron shell can hold up a maximum of 8 electrons. So you have to remember that this first electron shell holds 2 electrons, and then the next electron shell is going to hold 8, and the next electron shell after that is also going to hold 8. You can see in this first picture that we have hydrogen represented, and hydrogen has 1 proton and 1 electron. So its first shell will only contain 1 electron. Carbon has an atomic number 6, which means it has 6 protons and 6 electrons. When we put the electrons into shells, the first shell holds only 2, and then the second shell will hold up to 8, but because carbon only has 6 electrons, you can see 1, 2, 3, 4, 5, 6, it will have 4 electrons in this outer shell and room for 4 more. Nitrogen has an atomic number of 7, so that means it has 7 protons. It will also have 7 electrons. So 2 in that first shell, then 1, 2, 3, 4, 5 in the outer shell. And oxygen has an atomic number 8, so 2 in the first shell, and then 1, 2, 3, 4, 5, 6 in its outer electron shell. The outer electron shell on all atoms has a special name. And that is, so outer electron shell has a special name, and that's called the valence shell. And the valence shell contains valence electrons. It is these valence electrons that interact with other valence electrons from other atoms to create chemical reactions. Now, looking back at the periodic table, not only is the periodic table organized by the number of proteins, which is the atomic number of each of the elements, but it's also organized by how many electron shells that an atom has. If you look at the rows of the periodic table, you can see that as you move down the rows, the number of electron shells increases. Row 1, which contains hydrogen and helium, has just 1 electron shell. Row 2 has 2 electron shells. Row 3, 3 electron shells, and row 4, 4 electron shells. These rows on the periodic table have a special name. A period is what we call a row on the periodic table, and it tells us the number of electron shells. So if you have an element that is in row 1 or period 1, you have 1 electron shell. Atoms that are found in period 2 have 2 electron shells, period 3, 3 electron shells, period 4, 4 electron shells. Now let's look at an element that's not stable. Let's look at hydrogen. Hydrogen is the first element on the periodic table. It has an atomic number of 1, which means it has 1 proton, and it also has 1 electron. So its first shell contains just 1 electron. So it has 1 valence electron in its outermost shell, and you can see that because it only has 1 shell, it's missing the second electron in order to be stable. Because hydrogen is missing an electron, it has space to accept an electron from another atom, and that means that hydrogen is reactive. It is not stable because it has room for more electrons in that valence shell. Another example is lithium. Lithium is found on the periodic table. It has an atomic number of 3, which means it has 3 protons and 3 electrons. So lithium's first shell contains 2 electrons, 2 of those 3 electrons, and then its second shell, its outermost shell, contains the third electron. But that means it has room for 7 more electrons. So again, lithium is highly reactive because it has a fairly empty valence shell. In order for hydrogen and lithium to become stable, it needs to gain electrons in order to fill this valence shell. Hydrogen needs 1 electron in order to fill its shell, and lithium needs 7 in order to fill its outer shell in order to become stable and non-reactive. This tendency for elements to want to become stable, to have a complete valence shell, is called the octet rule. And the octet rule says that atoms are the most stable when they have full valence shells. A full valence shell. Now, if your valence shell is the first shell, like helium only has 1 valence shell, 2 is the full complement of valence electrons for that shell. But most shells after that first shell hold 8. So that's where that octet comes from. It takes 8 valence electrons to fill a shell, unless of course we're talking about the first valence shell, which can only hold 2. But the octet rule tells us that in order to be stable, an atom wants to have a full valence shell of electrons. Now when an atom does not have a full valence shell, it wants to combine with other atoms to form a compound to become stable. And there are 2 types of compounds that exist when atoms come together. The first type of compound is called an ionic compound, and the second type of compound is called a molecular compound. And the difference between an ionic compound and a molecular compound is what happens with the valence electrons. In ionic compounds, atoms form ionic bonds where electrons leave one atom and go to another atom. So one atom loses an electron and one atom gains an electron, and through that the 2 atoms are bonded together through an ionic bond. In ionic compounds, it will involve a metal, in this case sodium, with a non-metal, chlorine. So ionic compounds are compounds that contain a metal and a non-metal, and we see that electrons are lost and gained in order to make the ionic bond. In a molecular compound, we are looking at only atoms that are non-metals. And when nonmetals bond together, what happens is that they share the electron. So instead of one atom losing an electron and another atom gaining an electron, we see that atoms will share electrons in molecular compounds. So ionic compounds involve a metal and a nonmetal, and molecular compounds only involve nonmetal atoms. For the rest of this video, we're going to look at ionic compounds more closely, and then in another video we'll look at molecular compounds. So ionic compounds involve a metal and a nonmetal coming together, and an analogy that I like to use is a high school cafeteria, or in this case I call it high school cool cafeteria for modeling ionic bonding. Let's imagine that each element is a table in the high school cafeteria. So here is our high school cafeteria, and each table represents an element on the periodic table. Now, the number of chairs around each of these element tables depends on the number of valence electrons in the atom of each of the elements. So for instance, for our potassium table, potassium has just one electron in its valence shell, so it only has one chair at its table, representing that one valence electron. Now the tables for helium and neon have 8 chairs because helium and neon are noble gases. They have full valence electron shells, which means that they have 8 valence electrons for neon and 2 valence electrons for helium. Remembering that helium only has 1 electron shell and holds just 2 electrons. So let me go ahead and put those chairs in for helium and for neon. Now for this analogy only, the coolest tables in this high school cafeteria are full tables. So helium is considered a full table because it has a full valence shell with 2 electrons. Neon is considered a cool table because it has its full table with 8 valence electrons in its outermost shell. So helium and neon are considered the cool tables, and they actually won't accept any more chairs or any more electrons at their table. They are stable. They're cool. They won't accept anything else. The other elements that are shown here don't have full tables, but they want to be cool, so they want to fill their tables with electrons. So I've gone ahead and drawn in the chairs for these other atoms, and you'll see that like potassium has 1 chair because it has just 1 valence electron. Selenium has 6 valence electrons, so it has 6 chairs. Sodium, 1 valence electron, 1 chair. So remembering that they all want to be cool. They want to have full tables. So in order to get full tables, what these elements that don't have full valence shells are going to do is that they're going to connect with other tables, with other elements to create full tables. So let's look at selenium here. It has 6 valence electrons. In order to get 8 chairs, it's going to look at other atoms who are going to donate their electrons. So potassium has 1 electron. It can give up that electron to selenium, and then selenium will gain an electron, and then this potassium here can also give up its electron, and then selenium will gain 2 electrons. It will now have 8 electrons in its outermost shell and will be connected to the 2 potassium tables. So this whole thing becomes a compound, and it is now stable because the selenium has its 8 chairs to make it a full table, or 8 valence electrons, and it got there because it took an electron from each of these atoms. Another example, we have sodium here, which has 1 chair or 1 valence electron, and we have chlorine here, which has 7 valence electrons. Now to figure out which table is going to donate its electrons, think of it this way. What's easier? Is it easier for chlorine to give up or move 7 of its chairs to sodium, or is it easier for sodium to give up its 1 chair and move to chlorine? Hopefully you can see that it's easier for sodium to give up its chair. And when sodium gives up its electron, its valence electron, and adds it to chlorine, chlorine now has a full valence electron shell or a full table. So sodium and chlorine come together to create a stable compound, a stable ionic compound. Another example is magnesium and sulfur. Magnesium has 2 electrons in its outermost shell. Sulfur has 6. And then when they bring their tables together, it's easier for magnesium to move its chairs to sulfur. And when it moves its chairs over to sulfur, sulfur becomes a full table with 8 electrons, and then the two tables are bonded together. So magnesium loses its 2 valence electrons, sulfur gains its 2 electrons, the tables get pushed together, and it creates a compound with magnesium and sulfur. So this analogy of the periodic table high school cafeteria model is a great way to visualize what's happening when ionic compounds are created. The idea that noble gases are stable with full valence shells, and therefore they don't bond with other atoms, they're not reactive, whereas atoms that don't have full valence shells, they are reactive because they're looking to fill their shells to become stable. And that's why ionic bonding happens. What we're going to do now is look at some ionic compounds more closely to see exactly what's happening with this loss and gain of electrons. So the first one that we're going to look at is example 1, which is sodium and chlorine. And how I'm going to represent sodium chlorine is very much like I did in the high school cafeteria. Sodium is its own table, and it has 1 valence electron, so 1 chair, and chlorine, the symbol for chlorine is Cl, and it has 7 valence electrons, so 7 chairs, like so. Now on the periodic table, sodium is a metal because it's on the left-hand side of the periodic table, and chlorine is considered a non-metal, and it's found on the right side of the table. Now looking at the electrons, which element would you say will give up its electron? Is it easier for chlorine to give up all 7 to sodium in order to make it have a full valence shell, or is it easier to move just 1 electron from sodium so that chlorine has a full valence shell? Hopefully you say that it's easier to move 1 electron than 7. So sodium is going to give up its electron to chlorine so that chlorine has its full valence shell. So we say that sodium loses 1 electron, so 1 electron, and chlorine gains 1 electron. When you lose an electron, an atom becomes more positive because the electron's negative. When you lose it, you become more positive because now you'll have more protons than electrons. When chlorine gains an electron, it becomes more negative because now it has more electrons than it has protons. So it's very important to get the idea that when you lose an electron, the atom becomes more positive, and when you gain an electron, the atom becomes more negative. Now to build on to the terminology, when an atom becomes positive, it has a special name called a cation. And when an atom gains an electron and becomes more negative, it's called an anion. And it's the cation and the anion that, when bound together through an ionic bond, create a compound. Why sodium and chlorine now stick together is because sodium is positive and chlorine is negative, and opposites attract. So now they are bonded together because they're attracted to each other because they have opposite charges. Sodium has a positive charge, chlorine now has a negative charge, and they are bound together in an ionic compound. The chemical formula for this compound is 1 sodium to 1 chlorine, and we show the 1-to-1 relationship in subscripts. It took 1 sodium and 1 chlorine to make this sodium chloride compound. Now the sodium chloride compound, which is shown by this Na1Cl1, can also just be written as NaCl without the 1 subscripts, because that's just assumed when you don't have any subscripts that it's 1-to-1. Let's look at another example. Example 2 has beryllium and oxygen. So I'm going to go ahead and show the valence electrons for each of these elements. So beryllium has 2 valence electrons and oxygen has 6 valence electrons in their outermost shell. Now, first of all, we have to look at these as beryllium is our metal and oxygen is our non-metal, and which one is going to give up its electrons and which one is going to gain its electrons. We know it's easier to give up electrons when you don't have as many. So looking at beryllium and oxygen, it's much easier for beryllium to give up its 2 electrons to make oxygen stable than oxygen giving up its 6 electrons to beryllium to make beryllium stable. So beryllium is going to lose 2 electrons. So I've written beryllium is losing 2 electrons. So that means it's going to have a charge of +2, because whenever you lose electrons, you become more positive. So beryllium now has a charge of +2, and oxygen is going to gain 2 electrons. Whoops. There we go. Oxygen gains 2 electrons, so it's going to have a charge of -2. So beryllium loses its 2 electrons to oxygen, and oxygen gains 2 electrons. So beryllium is going to be our cation, meaning it's now positive, and it has a charge of +2, again because it loses its negative electrons. Oxygen is the anion because it has a charge of -2 from gaining those 2 negative electrons. So when we write the chemical equation for this, it takes 1 beryllium and 1 oxygen in order to create a stable ionic compound. Now we don't have to write the ones in because they are assumed, so it's just 1 beryllium, 1 oxygen, and then the compound name for this becomes beryllium. We always list the metal first, and then oxide, and you can see that we use the ending IDE on the non-metal when we name the compound. So beryllium oxide and beryllium and oxygen combine in a 1-to-1 ratio. Now in our next example we have calcium and phosphorus, and calcium has 2 valence electrons in its outer shell, and phosphorus has 5 valence electrons in its outermost shell. So we can see here that its calcium is going to lose its 2 electrons and give it to phosphorus. And then phosphorus, from gaining those electrons, will have 1, 2, 3, 4, 5, 6, 7 valence electrons in its outermost shell. So it's still missing 1 electron right here. So let's see how that works. So first of all, calcium loses electrons, so it's losing 2 electrons. That means it's going to have a charge of +2 because it becomes more positive. Phosphorus, on the other hand, wants to gain 3 electrons in order to have a full valence shell. So you can see here that it needs 1, 2, 3 electrons in order to become stable. So that means that it has a charge of -3. When calcium gives up 2 electrons, it becomes stable because it no longer has that valence electron shell. Phosphorus, though, is not quite stable yet because it's still missing 1 electron. So in order to create a compound, we need to add another calcium atom. So I'm going to go ahead and do that. I'm going to create a new calcium atom with 2 valence electrons, and one of these valence electrons will then go to that phosphorus atom, and now the phosphorus atom has 3 valence electrons, so it's stable. So this first calcium atom is now stable, this phosphorus atom here is stable, but this second calcium atom now only has 1 electron in its valence shell. So I'm going to create another phosphorus atom to accept that 1 lone electron. So here's a second phosphorus atom with 5 valence electrons. I'm going to lose that calcium electron to this phosphorus. And that leaves this second phosphorus with two positions left open for valence electrons. So that means it's going to take one more calcium atom with its two valence electrons that it's then going to give up to the last two positions here in the phosphorus. And now all of our metal atoms and our non-metal atoms are now stable. So in this case, it took 3 calciums to 2 phosphorus to make this calcium phosphoride compound. So this becomes calcium phosphide, I should say. So calcium phosphide is this ionic compound, and it took 3 calciums to 2 phosphorus to create a stable compound. Now what's interesting about these subscripts is that it tells you how many atoms it takes in order to make the stable compound. But if we were to add the ionic charges, so we said calcium has a charge of +2 and phosphorus has a charge of -3. Can you see that if you bring them down and cross them, you can see what the ratio of atoms is going to be in the compound, and that works for all ionic compounds. If you know the ionic charges, whether they're positive and negative, and you know the numeric value, so calcium's +2 and phosphorus is -3, because calcium is losing 2 electrons and phosphorus needs to gain 3 electrons, you can bring them down and cross them over, and then you find out the subscripts. Let's see what we mean in terms of the magnesium and nitrogen. So looking at magnesium, we see that it has 2 electrons in its outer shell. So that means in order to be stable, it wants to lose 2 electrons, and when you lose 2 electrons, your charge becomes +2. So magnesium is the metal ion in this combination, and nitrogen has 1, 2, 3, 4, 5 valence electrons, so it wants to gain 3 electrons, and whenever you gain electrons you become more negative because electrons are negative, so it has a charge of -3. That's its ionic charge. So when we're looking at how many magnesiums come together with the number of nitrogens, I write it with the charges up top. And then to figure out what the ratio is, I'm going to bring down the magnesium charge and put it as a subscript without the sign with the nitrogen. And then I'm going to bring down nitrogen's charge and make it the subscript of magnesium without the sign. So that means that magnesium, it takes 3 magnesiums and 2 nitrogens to create magnesium nitride. So it looks like that, and then we call that magnesium. So we keep the full name of the metal, and then nitrogen becomes nitride, that IDE ending, because it's an ionic compound. Now there's an easy way to find the ionic charge of a compound without actually having to draw out the atom with all the shells and then counting up the valence electrons. The nice thing about the periodic table is not only is it organized by mass and the number of protons and electrons it has, but it's also organized in terms of periods, which we saw before. So the periods are the rows, and the rows tell us how many electron shells we have. So hydrogen and helium are in period 1, so there's 1 electron shell, 2 electron shells for the second row, 3 electron shells for the fourth row, and so on and so forth. And you can write that right on your periodic table if you want. That period is equal to the number of shells. Now the columns are called the groups, and the group numbers, each group has the same number of valence electrons. So if we look at group 1A, we say that group 1A has 1 valence electron in its shell, and because it only has 1 valence electron, that means it wants to lose that 1 electron. So its ionic charge in the full column here is going to be +1. That means that this first shell is very, very reactive. In group 2, there are 2 valence electrons. So it's going to want to lose those 2 valence electrons. So all of the atoms in this group 2 have a charge of positive 2. And it just so happens that these 2 groups are our metals, and they are highly reactive. As we move to the right of the periodic table, we move from metals to our transition metals. Now, transition metals, it's interesting how their valence electrons react, and some of those electrons that are way out further from the nucleus, they seem to jump from one electron shell to another, and so it's harder to figure out the valence electrons there. And we'll be talking more about those transition elements in ionic compounds later on. But these are metals. They're just called transition metals. Now, our last group of metals that we're going to work with are our group 3 metals. And our group 3 metals have a charge of positive 3, which means they have 3 valence electrons in their outermost shell, and therefore they have the positive 3. After that, our group 4, 5, 6, 7, and 8, these are our nonmetals. So we have metals on this side, which are going to have a positive charge, and then our nonmetals are over here on the far right, and they're all going to have a negative charge. And remember, now because these are nonmetals, they're going to want to gain electrons. So when we talk about the group 4 and the nonmetals here, we're looking at the fact that they have 4 valence electrons, and because they have 4 valence electrons, they want to gain 4 in order to be stable. Group 5 have 5 valence electrons, so they're going to want to gain 3 electrons to be stable. Group 6 have 6 valence electrons, so they want to gain 2 electrons to be stable. Group 7 have 7 valence electrons, so they only want to gain 1 electron. And then group 8, which is the final group, they have 8 valence electrons in their shell, so they have a full shell, so they're stable, so they don't need any, so they don't have a charge. You can write these charges on your periodic table in your textbook, and therefore when you are looking at ionic compounds and you want to know the charges, it's easy. You just have to find the compound and then look to see what group they are in, and because you've already written the charges, you know that all of group 1 has a charge of positive 1, all of group 2 has a charge of positive 2, all of group 3, positive 3. Well, I should say metals. Sorry, not your metals have those, so aluminum, gallium, and so on. Negative 4 is going to be your charge on your nonmetals, and your nonmetals are all in red. So this is a fast way to look up charges without having to actually draw the valence shells. So one of the skills you need to know for this unit is if you are given the compound formula, to be able to write the name of the compound. So looking at this first compound, we have CS combining with Cl, and there aren't any subscripts, and when there aren't subscripts for a chemical formula, we just assume it to be a 1-to-1 ratio. And the name is going to be the name of this first element, the full name. We always write the metal first. So cesium is our metal, and how I know that that is cesium is I look up the CS on the periodic table and I write its full name because it is the metal, and then the Cl stands for chlorine, and I see that's a non-metal on my periodic table, so I end it with IDE. So cesium chloride is the name of this chemical compound. My next chemical compound, I have Sr, which stands for strontium, which is a metal, so I write the full name. And it combines with bromine, and bromine is my non-metal, so bromine becomes bromide. So this is strontium bromide. K stands for potassium, So I write out the full name, and O stands for oxygen, which is my nonmetal, so I change it from oxygen to oxide. And then my last one, Li, stands for lithium, and fluorine is the nonmetal, and that becomes fluoride, so lithium fluoride. Also, if you're given the name, you need to be able to give the formula. So I have sodium sulfide. So the first thing I'm going to do is look up the symbols for each of these. Sodium is a metal with the symbol Na, and sulfide stands for sulfur, which is the nonmetal. The next thing I need to do is go on to my periodic table and look up the ionic charges. Sodium is in group 1, so that means it has one valence electron that it's going to want to lose, so it has a charge of +1. And then we can look up sulfur, which is a nonmetal, and it's in group 6, so it's going to have a charge of -2 because it's going to want to gain 2 electrons. And then by crossing over, I bring the 2 down from the sulfur and put it with the sodium, and the 1 down from the sodium and put it on the sulfur. So it says that sodium and sulfur come together in a 2-to-1 ratio. So my chemical compound for this is going to be Na2S. I don't have to write the 1 for that one. Magnesium chloride, the symbol for magnesium is Mg, and the symbol for chlorine is Cl. Magnesium is in group 2, so that means it has a charge of +2 because it wants to lose 2 electrons. And chlorine is in group 7, which means that it has 7 valence electrons, so it wants to gain 1 more valence electron in order to be stable, so it has a charge of -1. Then using my crossover method, I'm going to put the 2 with the chlorine and the 1 with the magnesium, so my chemical formula is MgCl2. You don't have to write 1 as the subscript for the magnesium. Calcium iodide, that's going to be a calcium coming together with an iodine atom. Calcium has a charge of +2 because it's in group 2 and it wants to lose 2 valence electrons. Iodine is in group 7, so it has a charge of -1 because it wants to gain 1 electron. Now when I use my crossover method, that 1 from the iodine goes with the calcium, and then the 2 from the calcium goes with the iodine. So my ionic compound formula is going to be CaI2. And lastly, barium selenide. Barium is in group 2, so it has a charge of +2. Selenide, which has the symbol Se, it is in group 6, so it has a charge of -2 because it wants to gain 2 electrons. And then by the crossover method, I bring them down. Now in this case, you can see that it takes 2 barium to 2 selenium, and that can be reduced to a 1-to-1 ratio. So we can just say BASE as our compound formula for that. So if you see that you have the same numbers here, and it's a 1-to-1 ratio, then you can just leave it as without any subscripts. So that's it for our introduction to ionic compounds. Our next part, we're going to be looking at transition metals that make up ionic compounds, and it's a little bit different in terms of how we put together our compound formulas. Thanks for watching.